A classical field theory is a physical theory that predicts how one or more physical fields interact with matter through field equations. The term classical field theory is commonly reserved for describing those physical theories that describe electromagnetism and gravitation, two of the fundamental forces of nature. Theories that incorporate quantum mechanics are called quantum field theories. A physical field can be thought of as the assignment of a physical quantity at each point of space and time. For example, in a weather forecast, the wind velocity during a day over a country is described by assigning a vector to each point in space. Each vector represents the direction of the movement of air at that point. As the day progresses, the directions in which the vectors point change as the directions of the wind change. From the mathematical viewpoint, classical fields are described by sections of fiber bundles. Descriptions of physical fields were given before the advent of relativity theory and then revised in light of this theory. Consequently, classical field theories are usually categorized as non-relativistic and relativistic. Modern field equations tend to be tensor equations. In 1839, James McCulloch presented field equations to describe reflection and refraction in an essay toward a dynamical theory of crystalline reflection and refraction. Non-relativistic field theories. Some of the simplest physical fields are vector force fields. Historically, the first time fields were taken seriously was with Faraday's lines of force when describing the electric field. The gravitational field was then similarly described. Newtonian gravitation. The first field theory of gravity was Newton's theory of gravitation, in which the mutual interaction between two masses obeys an inverse square law. This was very useful for predicting the motion of planets around the Sun. Any massive body M has a gravitational field G which describes its influence on other massive bodies. The gravitational field of M at a point r in space is found by determining the force F that M exerts on a small test mass M located at r, and then dividing by M. Stipulating that M is much smaller than M ensures that the presence of M has a negligible influence on the behavior of M. According to Newton's law of universal gravitation, F is given by where as a unit vector pointing along the line from M to M, and G is Newton's gravitational constant. Therefore, the gravitational field of M is the experimental observation that inertial mass and gravitational mass are equal to unprecedented levels of accuracy, leads to the identification of the gravitational field strength as identical to the acceleration experienced by a particle. This is the starting point of the equivalence principle, which leads to general relativity. For a discrete collection of masses, m, located at points r, the gravitational field at a point r due to the masses is if we have a continuous mass distribution ρ instead, the sum is replaced by an integral. Note that the direction of the field points from the position r to the position of the masses r. This is ensured by the minus sign. In a nutshell, this means all masses attract. In the integral form, Gauss's law for gravity is, while in differential form it is therefore. The gravitational field G can be written in terms of the gradient of a gravitational potential phi. This is a consequence of the gravitational force F being conservative. Electromagnetism. Electrostatics. A charged test particle with charge Q experiences a force F based solely on its charge. We can similarly describe the electric field E so that F equals QE. Using this and Coulomb's law, the electric field due to a single charged particle is the electric field is conservative, and hence is given by the gradient of a scalar potential. V. Gauss's law for electricity is in integral form, while in differential form. Magnetostatics. A steady current I flowing along a path will exert a force on nearby charged particles that is quantitatively different from the electric field force described above. The force exerted by I on a nearby charge q with velocity v is where B is the magnetic field, which is determined from I by the Biot-Savart law. The magnetic field is not conservative in general, and hence cannot usually be written in terms of a scalar potential. However, it can be written in terms of a vector potential. Gauss's law for magnetism in integral form is, while in differential form it is. The physical interpretation is that there are no magnetic monopoles. Electrodynamics in general, in the presence of both a charge density ρ and current density J, there will be both an electric and a magnetic field, and both will vary in time. They are determined by Maxwell's equations, a set of differential equations which directly relate E and B to the electric charge density ρ and current density J. Alternatively, one can describe the system in terms of its scalar and vector potentials V and A. A set of integral equations known as retarded potentials allow one to calculate V and A from ρ and J, and from there the electric and magnetic fields are determined via the relations hydrodynamics. Fluid dynamics has fields of pressure, density, and flow rate that are connected by conservation laws for energy and momentum. The mass continuity equation is a continuity equation representing the conservation of mass, and the Navier-Stokes equations represent the conservation of momentum in the fluid. Found from Newton's laws apply to the fluid. If the density ρ, pressure P, deviatoric stress tensor tau of the fluid, as well as external body forces B, are all given, the velocity field U is the vector field to solve for potential theory. The term potential theory arises from the fact that, in 19th-century physics, the fundamental forces of nature were believed to be derived from scalar potentials which satisfied Laplace's equation. Poisson addressed the question of the stability of the planetary orbits, which had already been settled by Lagrange to the first degree of approximation from the perturbation forces, and derived the Poisson's equation, named after him. The general form of this equation is where sigma is a source function and phi the scalar potential to solve for. In Newtonian gravitation, masses are the sources of the field, so that field lines terminate at objects that have mass. Similarly, charges are the sources and sinks of electrostatic fields. Positive charges emanate electric field lines, and field lines terminate at negative charges. These field concepts are also illustrated in the general divergence theorem, specifically Gauss's laws for gravity and electricity. For the cases of time-independent gravity and electromagnetism, the fields are gradients of corresponding potentials, so substituting these into Gauss' law for each case obtains where ρg is the mass density and ρe the charge density. Incidentally, this similarity arises from the similarity between Newton's law of gravitation and Coulomb's law. In the case where there is no source term, these potentials obey Laplace's equation. For a distribution of mass, the potential can be expanded in a series of spherical harmonics, and the nth term in the series can be viewed as a potential arising from the two n moments. For many purposes only the monopole, dipole, and quadrupole terms are needed in calculations. Relativistic field theory. Modern formulations of classical field theories generally require Lorentz covariance, as this is now recognized as a fundamental aspect of nature. A field theory tends to be expressed mathematically by using Lagrangians. This is a function that, when subjected to an action principle, gives rise to the field equations and a conservation law for the theory. The action is a Lorentz scalar, from which the field equations and symmetries can be readily derived. Throughout we use units such that the speed of light in vacuum is 1, i.e., c equals 1. Lagrangian dynamics. Given the field tensor phi, a scalar called the Lagrangian density can be constructed from phi and its derivatives. From this density, the functional action can be constructed by integrating over spacetime, whereas viewed as the Jacobian, in curved spacetime. Therefore the Lagrangian itself is equal to the integral of the Lagrangian density over all space. Then by enforcing the action principle, the Euler-Lagrange equations are obtained. Relativistic fields. Two of the most well-known Lorentz covariant classical field theories are now described. Electromagnetism. Historically, the first field theories were those describing the electric and magnetic fields. After numerous experiments, it was found that these two fields were related, or, in fact, two aspects of the same field. The electromagnetic field. Maxwell's theory of electromagnetism describes the interaction of charged matter with the electromagnetic field. The first formulation of this field theory used vector fields to describe the electric and magnetic fields. With the advent of special relativity, a more complete formulation using tensor fields was found. Instead of using two vector fields describing the electric and magnetic fields, a tensor field representing these two fields together is used. The electromagnetic potential is defined to be AA equals, and the electromagnetic current ER equals. The electromagnetic field at any point in spacetime is described by the antisymmetric rank electromagnetic field tensor, the Lagrangian. To obtain the dynamics for this field, we try and construct a scalar from the field. In the vacuum, we can use gauge field theory to get the interaction term. And this gives us the equations. To obtain the field equations, the electromagnetic tensor in the Lagrangian density needs to be replaced by its definition in terms of the four potential A, and it's this potential which enter the Euler-Lagrange equations. The M field F is not varied in the L equations. Therefore, evaluating the derivative of the Lagrangian density with respect to the field components and the derivatives of the field components obtains Maxwell's equations in vacuum. The source equations are, while the other two are obtained from the fact that F is the curl of A, where the comma indicates a partial derivative. Gravitation. After Newtonian gravitation was found to be inconsistent with special relativity, Albert Einstein formulated a new theory of gravitation called general relativity. This treats gravitation as a geometric phenomenon caused by masses and represents the gravitational field mathematically by a tensor field called the metric tensor. The Einstein field equations describe how this curvature is produced. Newtonian gravitation is now superseded by Einstein's theory of general relativity, in which gravitation is thought of as being due to a curved space-time caused by masses. The Einstein field equation describes how this curvature is produced by masses where kappa equals 8 pi g. C4 is a constant which appears in the Einstein field equations, and is the Einstein tensor. The vacuum solution can be obtained by varying the following Einstein-Hilbert action with respect to the metric. The vacuum field equations are the field equations written without matter. Solutions of the vacuum field equations are called vacuum solutions. The field equations may be derived by using the Einstein-Hilbert action, varying the Lagrangian where R equals rab. Gab is the Ricci scalar written in terms of the Ricci tensor rab, and G, the determinant of the metric tensor gab, will yield the vacuum field equations. Unification attempts. The Kaluza-Klein theory attempts to unify gravitation and electromagnetism in a five-dimensional spacetime.